Welcome to Thermodynamics. Uh, my name is Dr. Chimobi Aluto, and I'll be taking you through this part of the module. So these are the textbooks which most of the work presented in this lecture were derived from, and this could also be used as a form of self-study for you as well. The last one, which is highlighted here, is the steam table, which you'll be using for most of your calculations. So what do we have here? The most of the lecture materials here were developed by the previous work of the previous lecturers, the late Dr. Zaki, Stephanie, and Dr. Ross. So what are the basic concepts of thermodynamics? So I'll start off by explaining what a system and control volumes are. So a thermodynamic system is a quantity of matter or region in space chosen for study. So the system is bounded by the boundary, and the boundary prevents the system, is a kind of a barrier between the system and the surrounding. Now, the control surface or the boundary could be either be real or imaginary, and in other cases, it could be fixed or movable. So systems and control volumes, the systems can be considered closed or open. A closed system is will always have a fixed amount of mass, and there will not be any mass going across the boundary. So, but a closed system can also have either a fixed boundary or a moving boundary. So, in the case of the examples given here, this is the moving boundary. And as we said, in a closed system, the mass of the content, the fluid within the system is fixed, but and mass cannot move in or move out, and that is what makes it a closed system. Okay, and the opposite of that would be for open system. So in an open system, this is where we encounter control volume. Okay, so the control volume is a selected region in space, as we explained when we explained what a system is. So this is usually noticed in systems like the nozzles, the water heater, and many more flow systems that involve a steady flow. Okay, so in this kind of system, both mass and energy can cross the boundary of the control volume. Now, the control volume in the case of a nozzle is indicated by this imaginary boundary. Okay, the boundary is imaginary depending on the type of flow that we have flowing through the nozzle. Similarly to this kind of a system with a moving boundary, and also an inlet to allow fluid to go in. Okay, a typical example of that is a water heater. When this tank is empty, the control volume remains imaginary, which is the shape of the inner part of the tank. Now, when the water fills up to the brim, then the heating activity occurs, and the hot water is collected at the top. Now, we refer to the remaining water, if it's a fully developed flow, okay, then we refer to that water in the tank as the control volume. Okay, so we go over to state and equilibrium. Now, I've mentioned in the previous slide about the different states of the flow. If is it a fully developed flow, or is it a flow at the beginning of the process? So, and in thermodynamics, we deal with equilibrium states. So, equilibrium state is a state of balance. So, this is where there are no unbalanced potentials or driving force within the system. So in the case of thermal equilibrium, as given in the example here, the example for A, you can see that within the system, in this case a closed system, uh, before the system reaches thermal equilibrium, if you take temperature reading at some different areas within the system, they will have different temperature reading. But after a period of time, obviously, then this temperature becomes uniform. And when the temperature reading is uniform across the system, then we can refer to this as being reaching a state of thermal equilibrium. Okay. So what is a thermodynamic process? A thermodynamic process is a change that a system undergoes from one equilibrium state to another equilibrium state. The process part is the series of states that a system passes through during a process. To describe a process completely, we need to specify the initial and the final states, the path it follows, and the interaction with the surrounding. So given the graph here for property A against property B. So for a thermodynamic process to move from state 1 to state 2, then it has to follow a path. And we need to specify what the initial and the final states are in order for us to recognize the path it follows. So example of a thermodynamic process. If a process it moves in case of compression, a slow compression, then the change in volume of the fluid within here will change ever so slightly. So that because of that infinitesimal change, we can regard this system as a quasi-equilibrium because the volume does not change fast enough for us to identify the difference in volume. But if the system, the process is very quick, the compression process is very quick, then we refer to this process as a non-quasi-equilibrium process. Okay. Now, what is a thermodynamic cycle? A system is said to have undergone a cycle if it returns to its initial state at the end of the process. For a cycle, the initial and the final states are identical. So, giving an example of a four-stroke engine. Here, at the intake end of the engine, a fuel injector inject fuel into the air intake. Now the air intake and the fuel mixes as a kind of a vapor, and it goes into this chamber. This chamber, okay, due to the motion of the piston, the rod, and the crankshaft, provides enough space to accommodate, to draw in the mixture of air and the fuel. And that is also helped by the opening of this valve here, the intake valve. Now, when this mixture of air and fuel goes in here, the crankshaft rotates clockwise to push. As it rotates clockwise, the upward motion of the rod and the piston, we compress this fluid up to the point where it meets the spark plug, and the spark plug ignites this mixture of air and fuel, and that forms a mini explosion, or in this explosion, which is a form of combustion, and that explosion expands, okay, expands the process, and that expansion process pushes the pressure of that expansion pushes this piston downward to the clockwise motion, and the crankshaft returns it, and the byproduct of the combustion, in this case, the exhaust gas, are pushed away. And as we said, in the cycle, the initial and the final state are identical. In this case, the initial state here is a mixture of air and vapor, air and fuel. Then at the exit is a byproduct of the combustion as well. Now, if you watch this YouTube video, it will give you a more explanation on how this four-stroke cycle engine works. Now, this is the same process represented on a pressure volume diagram. Okay, on the PV diagram, the fuel and air mixture comes in at the atmospheric pressure, and when that goes into the system, the quick compression. Okay, this is the intake. The fuel and the air goes in at constant atmospheric pressure, and what happens at point 2? The piston compresses it Okay, and that compression increases the pressure within the system, and as it hits the spark plug at this point, the ignition due to the spark plug causes explosion. That explosion causes a very quick rise in pressure, which is the expansion due to the combustion or the explosion in the mini explosion in this case. And when that happens, the crankshaft returns as the pressure dissipates, returns, and the exit valve opens, and the exhaust gases are pushed away, and the pressure returns back to its original, and the system continues because it's a cycle. It continues in that motion. So the thermodynamics, how do we represent cycles on a diagram? So like I've already explained, we can use the pressure volume diagrams, and we can use the temperature entropy diagram. We can also use the temperature volume diagram, depending on what we are dealing, the physical properties we are dealing with. So the thermodynamic cycles, here we have three systems, one, two, three. So what do they all have in common? Okay, what they have in common is that they all perform on a thermodynamic cycle. Okay, so the power generation and refrigeration, they all operate on power dynamic cycles. So here, the working fluid undergoes a series of property change before returning to its original condition. The cycle is repeated endlessly. Useful work or heat transfer takes place. Now, in the case of refrigeration, we already know what happens. The hot air within the refrigerated chamber is extracted by a cold fluid through a heat exchanger coils, and in this case, in the power station, the steam is generated, and that steam is used to move turbines to generate electricity. And in the steam turbine is a mixture of air and fuel generates enough energy to give the jet a thrust in order to move. Okay, so thermodynamic cycles can be divided into two general categories: the power cycles and refrigeration cycles. The devices or systems used to produce a net power output are often called engines, and the thermodynamic cycle they operate on are called power cycles. The devices or system used to produce refrigeration are called refrigerators, air conditioners, heat pumps, and the cycles they operate are called the refrigeration cycle. So the thermodynamic cycles can be categorized another way, a closed and open cycle. In closed cycles, the working fluid is returned to initial state at the end of the cycle and is recirculated. A little bit more on this in the next slides. So in open cycles, the working fluid is renewed at the end of each cycle instead of being circulated. So typical example, a car engine, which we've already given you example of four-stroke uh, engine system. The combustion gases are exhausted and replaced by fresh air fuel mixture at the end of each cycle. And that is why and this is also categorized as a power cycle engine because all we need them for is power engines. So we replenish the fuel for running the car, and also when we're driving the car as well, takes in air in order to mix with the air to for the process to work. So thermodynamic cycle can also be categorized as a gas cycle or vapor cycles. Depending on the phase of the working fluid, the working fluid here refers to the substance that circulates through the cyclic device. Okay, so like we mentioned in gas cycles, what enters here is the vapor, more or less, through the fuel injector, the vapor and the vapor of the fuel and the air mixture, which we can refer to as the gaseous state. And after the process of igniting this mixture, what leaves the engine is an exhaust gas. So the working fluid remains in gas phase. Now, what about the vapor phase? The difference between the gas phase and the vapor phase is that in the vapor phase or the vapor cycle, the working fluid can exist as a liquid and also as a vapor. A typical example of that is the power plant. So initially, water is boiled to generate steam, and that steam is used to move a turbine. The turbine is used to move engines to generate electricity, and the low quality steam leaving the turbine is returned to this cooling tower where they are condensed into liquid, and the process continues. And the water is also pumped back into the boiler to generate steam again, and the cyclic uh, process continues. Bringing us to the first law of thermodynamics. Now, what is the first law of thermodynamics? The first law of thermodynamics concerns mainly to the conservation of energy. And as you can know, as we know, energy can neither be created nor destroyed, but can change from one form to another. But in all processes, the energy is conserved. And what do we mean by that? In the example given here, every matter or material possesses potential energy as long as there's a difference in height wherever it's situated. Now, if that potential energy has a unit of 10, if it falls from a height due to that motion of the matter or the mass falling, uh, the potential it will lose some of its potential energy, and that some of the potential energy that it loses becomes kinetic energy, and that kinetic energy is as a result of the motion. Okay, now remember what we said. The first law makes sure that whichever potential energy that is lost will be transformed to kinetic energy, meaning that if the object possessed a potential energy with a equal unit of 10% of 10, then it means that if it loses 3 units of potential energy, that 3 units will become the kinetic energy. Okay, and that has to equal the original total number of energy possessed initially. So the steady flow energy equation in this kind of system will be given as this, where Q is the heat transfer minus the work done by the system or to the system, equals to the mass of the material multiplied by the potential energy, the kinetic energy, and the enthalpy. Okay, and all the variables here has their unit represented here. And as you can see, all the units are in SI unit. So in a flow system where there is a movement in fluid, okay, and there is difference in height as well, then the same equation is now modified to account for the movement, the flow of the material, in this case the fluid, through the system with respect to time. So therefore, the heat transfer now becomes a heat transfer rate, and it has a unit of joules per second, which is exactly as watts. Same as the work done by the system, it becomes the work transfer rate, which also has the SI unit of joules per second, equivalent to watt. Then the mass in this case becomes the mass flow rate due to the movement in the system. So the mass flow rate has a unit of kilogram per second. Then everything else remains the same. So for a system that is stationary, then the energy balance is given as the heat transfer rate minus the work transfer is equal to the internal energy that the system possessed, that the material itself possessed. And this could be broken down into the mass times the specific internal energy, which is equal to the internal energy per unit mass. Okay, and it has a unit of joules per kilogram. The second law and entropy. Now, the second law, second law will help us, because since we already know that the first law is all about the conservation of energy, and that energy can change from one form to another. But what it doesn't tell us is to which direction does energy favor? The change in energy from one form to another, to which direction does it go? The second law of thermodynamics helps us understand this. So with the example given here, a glass cup will always and most likely move from being like this to being shattered, rather than the other way around. Okay, so why is it? As we've already stated, some of the examples here. Now, with this example of a cable, okay, let's say this wire, we know that mostly what we transport with wire is electrical energy. Now, during the process of transferring electrical energy through wires, there is always, all of us must have experienced it, there's always some some of that electrical energy that is converted to heat, so leaving from the wire. Now, if there is zero current passing through this wire, which means there is no electrical energy passing through this wire, and you apply a heat from the environment onto that wire, you will never have electrical energy as a result of the heat being applied to it. Okay, does that make sense? So you can always have heat released from this wire if there is electrical energy passing through, because some of that electrical energy will be lost as heat to the environment. But the opposite direction is not going to happen. So similarly, in this system with a paddle and a kind of mechanical system to move the paddle. Let's say this mechanical system is stationary and this rotary wheel here and the paddles are not moving. Now, if you apply heat around the surrounding of this paddle, the heat here will not cause this paddle to move. Rather, if this system is moving, is in operation, then the friction generated by this movement of this paddle and other things can lose the mechanical energy here could lost. Some part of the mechanical energy could be lost as a form of heat. So this is why the second law helps us to know the direction of the process. Okay, so this brings us to entropy. So the entropy is the degree of disorderliness of a process. So in a highly ordered process, which is presented by this, could always increase its entropy by spreading, and the more it spreads, the more disordered it is, the higher the entropy it has. Okay, now this is very important for us. So uh, it is difficult to give a physical description of what entropy is without considering the microscopic state of the system. Now, for a highly ordered system, which we can see in these two images here, these are all sand castle, and a simplified sand castle. So because it's highly ordered, it has a very low entropy, which means that there is only few ways for us to reorder the microscopic parts of this sandcastle without changing the entire structure. Simply meaning that if wind starts moving away the smallest particles of this sand over a small period of time, over a certain period of time, this well-defined, detailed sandcastle will turn to pile of sand, okay? Which means that a highly ordered system with low entropy, the movement of the microscopic part will always change, okay, the structure of the system itself. It will not be recognized as a detailed sandcastle, it will just be recognized as a pile of sand. Then, but the other way around, if the system is highly disordered, like this pile of sand, then there are many ways for us to change the microscopic part of this sand without actually changing the structure, because the structure is just a pile of sand. Okay, so entropy always tells us that everything will continually increase in the universe as energy becomes more and more disorganized. So the sandcastle that is highly detailed will always tend to go this direction, okay, which is going back to pile of sand. So this is a video on YouTube by Brian Cox. I think it's a show, BBC show, where he explains this phenomenon. So if you have a chance, you can click on the link here and watch the video for more understanding on this entropy. Okay. So what are the uses of the second law? The second law may be used to identify the direction of process. And the second law also asserts that the energy has quality as well as quantity. Since we know that in first law that energy is concerned with the quantity of the energy and the transformation of the energy from one form to another, but we don't know, the first law does not tell us about that quality of energy. Okay, so but the second law provides us the means to determine the quality as well as the degree of degradation of the energy during the process. Then the second law of thermodynamics is also used in determining the theoretical limits for performance of commonly used engineering systems like heat engines and refrigerator. And these theoretical limits are referred to as the efficiency. Okay, so this brings us to the second law itself. So the second law states that it's impossible to construct a system which will operate in a cycle, extract heat from a reservoir, and do an equivalent amount of work on the surrounding. So meaning that some part of the heat extracted from the reservoir has to be lost. So meaning that the 100% of the energy extracted to perform the work will not convert, all of that heat will not convert to work. Some of it has to be lost. That's what the second law is trying to propose. And if we know the amount that is lost and the amount of the heat that is used to do, that the system used to do, perform the work, then we can easily identify the quality or the efficiency of the system. So with that, we can write the formula for efficiency, which is the net work produced by the system divided by the total heat supplied to the system. And this figure is always less than 100%. So in a system with flows of heat and work across the system boundaries, the heat flows causes a change in entropy of the system. So the rate of entropy change is given as Q dot. This is the rate of heat transfer divided by the absolute thermodynamic temperature of the system at the point of the heat flow. Okay, and in the system where the process is accompanied by mass flow across the boundaries, the flow of material into and out of the system through the boundaries will contribute to the total change in entropy. Each element of the material entering or leaving the system carries its own entropy, the same way it carries its own internal energy and enthalpy. And all these figures could be seen on the steam table. Okay, some of you who have done ITF, Introduction to Thermal Fluids, you must have been introduced to steam table and properties of steam. So you should know that all these elements have their own entropy, their internal energy and entropy, and all of these are tied to their other physical properties like their temperature and pressure. So entropy for a total reversible system is given as the integral of change in the heat transfer rate divided by temperature equals 0. So when a system undergoes an irreversible process from one equilibrium state to another, then the change in entropy is given by the integral of the heat transfer rate over the temperature. So thermodynamic processes. So these are some of the thermodynamic processes, and these are let's starting from the isochoric process. The isochoric process is when the system has a constant volume, and in this case, we can use other properties like the pressure and temperature, which are the changing variables now to represent the system, and that is given as the P1, which is the inlet. One here means the initial, and two in this case means the final. So it's given as P1 over T1 minus P2 over T2. And P and T are pressures and temperature, okay? These are equal to constant. And this equation is referred to as the Monton's law. Now, for us to move a particular fluid, okay, from point A to increase the pressure of a particular fluid from point A to point B while the volume remains constant, now we need to perform a certain amount of work, and that work is given as what? The integral of the change in pressure, the integral of the pressure times the infinitesimal change in volume, because the volume is constant, okay? Now, but the pressure varies, then the whole equation should be equal 0, okay? Now, what about an isochoric process? The example of isochoric process given from the Monton's law, we have an example here. An aircraft tire has a volume of 360 liters. Initially, the gas in the tire has a temperature of 14 degrees Celsius and a pressure of 3 bar. During takeoff, by the end of the runway, the temperature of the gas has increased to 23 degrees Celsius. What is the pressure in the tire? So from the Monton's law, we can record the known variables. So the initial pressure in the tire is 3 bar. The initial temperature of the tire is 14 degrees Celsius. We need to convert this to Kelvin because most of our calculation and the physical properties are based off of Kelvin. So we need to convert that temperature to Kelvin. Then we know the final temperature, which is 20 degrees C, but we don't know the final pressure. Now going to the Monton's law, we make P2, which is the final pressure, the subject of formula, and the equation becomes the T2 times P1 all divided by T1, and plugging in the known values, the variables, the values of the known variables, then we can solve for P2. So the increase in pressure from 3 bar is only by 0.094 bar, okay? So in an isobaric process is one in which the system has a constant pressure. And by so doing, the changing variables will be the temperature and the volume of the initial temperature and the initial volume of the system. Now, that is represented by the Charles law and is given as the V1 over T1 equal V2 over T2 all equal constant. Now, for us to move, for us to increase the volume of a particular fluid from point A to point B while the pressure remains constant, a certain amount of work has to be done, and that work is given as what? The integral of pressure by the change in volume. Now, as we can see, the pressure remains constant, so we move it out of the integral. Then we do the integral with respect to the initial and the final state, and that is given the final answer. The final equation becomes the pressure, the constant pressure here, times the final volume minus the initial volume. So the isothermal process, as the name implies, the temperature remains constant in this kind of system. And when this temperature remains constant, then the pressure and the volume becomes the variables, the changing variables. Now, that is given by Boyle's law, which is the P1 V1 equal P2 V2 equal constant. Now, in a system where we need to expand the fluid from point A to point B by reducing the pressure from point A to point B, then a certain amount of work has to be done. And that work is given as rho P, is given as the integral of pressure times the changing volume. So a typical example of a isothermal process. Here we have a sample of gas which has its initial pressure as 7.07 bar and a volume of 8.21 liters. It is expanded isothermally to a pressure of 2.65 bar. What is the new volume of this gas? Now we know about compression and expansion. So if we use the formula provided here, then we make the new volume, which is the final volume V2, subject of formula, and the formula becomes P1 times V1 all over P2, and we plug in the known variables and we calculate for the new volume. So, and as we expected, the volume increases due to the reduction in pressure. Okay. So, adiabatic process. When do we refer a system or process to be adiabatic? This is when there is no heat transfer. So, no heat transfer meaning there is no heat added to the process or removed from the process. Now, this does not mean that temperature cannot change, because in adiabatic process, there are in different processes could be adiabatic, but the properties or the characteristics of those processes can also lead to an increase in temperature or decrease in temperature. For those of you who have done things about reaction, especially chemical engineers, you will know there are some reactions that are endothermic or exothermic. So a reacting process could also be adiabatic, even though the reactants will always react to form an exothermic reaction or endothermic reaction. Okay. So the exothermic or endothermic reaction will lead to the increase in temperature or the decrease in temperature as a result of the reaction, the reaction process, but there is no heat added to the system or removed from the system. Okay. So, and this is given with this equation here, the P1 V1. So meaning that all the physical properties here, including volume, are all changing. So P1 V1 over T1 is equal to P2 V2 over T2, all equal constant. Now we can rewrite this equation if temperature is not known, and we can write it as P1 V1 raised to power gamma equal P2 V2 raised to power gamma and equal to constant. Here gamma refers to the specific heat ratio, and this specific heat ratio is a division of the specific heat capacity with respect to pressure by the specific heat capacity with respect to the volume. And in most cases, most of the fluid materials that we discuss, they all have their specific heat ratio known. They have known specific heat ratio, and there is a table where these numbers are given for the different fluid materials. And in this case, air has a 1.4 which is a unitless uh, unitless value for the specific iteration. Now, for a system to move from isothermic to isothermal to adiabatic, now from a PV diagram, uh, there has to be a certain amount of work done to that system to achieve this. So that is given as the integral of the pressure and the change in the volume. Okay. So an isentropic process is one in which there are no changes in the entropy. Now, this is a very important one, and we'll be using this quite a lot in our calculations. So, in an isentropic process, we know that this process is also an adiabatic process, which means that no heat transfer, heat is not added or removed. An isentropic process is also reversible. Now, for a system to be reversible, okay, we refer to this as an ideal process, and it is also not possible to actually achieve a perfectly isentropic process. But in most cases, we achieve some level of isentropic process, but not a perfect isentropic process. A typical example of this will be the turbine. Okay, the turbine system. If you pass a high quality steam, a superheated steam to a turbine, it will help generate to move the paddles, to move the turbine to generate electricity. But in the turbine, it is always good to maintain the fluid passing through the turbine as gas. Now, but the quality of the steam that goes into the turbine is not the same as the quality of the steam that leaves the system. So meaning that the perfect isentropy is not maintained because the quality of the steam leaving the turbine system will always be a low quality steam, no matter what you do, because some of the heat will be lost in the process. Some of the energy is lost in the process as well. So steam. So this is a TV diagram that explains how steam is generated. So uh, on a TV diagram, on this side of the curve, we have compressed liquid. Okay, the compressed liquid, as the temperature of the compressed liquid is increased, it is obviously by means of heat supply. Then the liquid becomes saturated, and as this liquid becomes saturated, it gets to a certain temperature where where all the liquid evaporates and becomes saturated vapor. Now the saturated vapor, the temperature falls while the pressure remains constant. Now if there is increase in temperature as the pressure remains constant, that saturated vapor becomes total so superheated vapor, and this is known as the superheated region. Now the region in between the critical point, which is the temperature at which all the saturated liquid converts to saturated vapor, exists a saturated liquid vapor region. Okay, this is where the substances exist as both liquid and also vapor mixture. Okay, now this explanation is very important because this explains how the steam table will be used, and some extracts from the steam table. So in the steam table, there are saturated water and steam, a section of the steam table, and there are superheated steam sections of the steam table, and also compressed water. In most cases, most of our calculations and our teaching will be within this region, the superheated steam and the saturated water and steam side of steam table. Okay. Now, saturated liquid vapor mixture. So to analyze a liquid vapor mixture, we need to know the proportions of the liquid and the vapor phase in the mixture. So this is done by defining the quality X as a ratio of the mass of the vapor to the total mass of the mixture, which is given as X is equal to the mass of the vapor divided by the total mass of the system, which is the mass of both the vapor and the liquid side of the saturated liquid side of the system. Now, if there is if the system contains a lot of saturated liquid, then the quality tends to go to zero. Now, if the system consists mainly of saturated vapor, then the quality is one. With this established, then it means that the more saturated vapor in the system, the higher quality, because the target here is what, the vapor phase, which is steam in this case. So the more water saturated liquid we have in the system, then the lower the quality of the steam. Like I explained with the steam going through a turbine system, right? So consider a tank that contains a saturated liquid vapor mixture. The volume occupied by the saturated liquid is referred to as VF. F here uh, is used to denote liquid, and the volume occupied by the saturated vapor is Vg. G here is denoted by gas or vapor. The total volume V is the sum of the two, which is total volume V is equal to Vf plus Vg. Now we can expand that. Since we know that volume, the unit of volume is meter cube. Now, if we know the mass, the total mass of the system, which is the fluid within the system, the mixture of liquid and vapor, then we call that MT, which is the mass total, the total mass, times the average specific volume. Now, what is the unit of specific volume? That is meter cube per kilogram. So if you multiply mass by the specific volume, you will be left with what? Meter cube. So if we expand this V equal Vf plus Vg, we can get a new equation for it, which is the mass times the specific volume of the average specific volume of the mixture equal to the mass of the fluid times the specific volume of the fluid plus the mass of the gas or the vapor times the specific volume of the vapor. Now, since we know that, what else can we do? From the knowledge of the quality, which we've already described in the previous slide, we said that X is equal to the mass of the gas over the total mass of the saturated liquid vapor mixture, right? Now, in that equation here, in this equation here, if we can make MF subject of formula in order to calculate, in order to get rid of the MF, then unify the MT and MG, then it becomes that the total mass of the system, which is equal to what? The mass of the fluid plus the mass of the gas. Then making MF subject of formula, then it becomes the total mass minus the mass of the gas or mass of the vapor in this case. Now we use this now to replace MF, right, in this equation, and the equation is expressed in this form. Now, if we know that the quality is the mass of the gas divided by the total mass, then we can make the mass of the gas subject of formula. Then it becomes mg is equal to x over mt. Now, if we plug that in this equation, wherever we see mg, we replace that by x over mt. So here we replace this with x over mt. Here we replace it with x over mt. Then what happens? First of all, open this bracket. Now, when you subtract mt minus x over mt, what do we have? We make lowest common factor. We have mt minus x all over mt. Then mt cancels mt, and you are left with what? 1 minus x. Then on this side, we replace it with the x over mt. Now, since we have 1 minus x in parentheses times Vf plus x over mt Vg all equal to mt average specific volume. Then if we take common factor here, the lowest common factor for the two things, then it becomes 1 minus x bracket Vf plus x Vg all over mt. So the mt cancels out, and we are left with what? The average specific volume of the system equal to 1 minus x close bracket specific volume of the fluid plus x times specific volume of the gas. Now, how do we expand this? So we open this bracket. So Vf multiplies 1, it becomes Vf minus x Vf plus x Vg. So what do? We now move the minus to subtract there, so it becomes Vf plus xvg minus xvf. So if we know xvg minus xvf is given as what? F of g. Okay, so we replace that in order to replace the when we open the bracket here. Okay, so when we do that, the equation now becomes simplified as this. So the average specific volume of the system is equal to the specific volume of the liquid plus x times specific volume of the liquid and gas. Okay, now we can make x subject of formula in order to find another way to calculate quality. Now, in the case that we don't know the mass of the gas and we don't know the total mass of the gas and the liquid, then we can use this particular specific volume of the fluid to calculate for the quality of the fluid, okay, the quality of the mixture. Now, we can also extend this to the enthalpy, and other physical properties that has a corresponding values for the given saturated temperature and pressure, or even superheated uh, temperature. Okay, so we can use that all of those physical properties available in the steam table to calculate for the quality of the system. Okay, so this brings us to the revision tutorial. So we'll be looking at some of the examples from the previous year when we did introduction to thermofluids, and hopefully this can bring back your memory, and we can move on from here. So a flow system does 150 kilowatt of work on the surrounding and loses 8 kilowatt of heat during the process. The fluid flows at a steady rate of 8 kilogram per second. The velocity at the inlet is 40 meter per second, and at the outlet is 5 meter per second. The inlet is 50 meter above the outlet. Calculate the change in potential energy per second, the change in kinetic energy per second, and the change in specific enthalpy. From the question, we know that it's a flow system. Then we know that the energy equation that we are going to use is for calculating the rate of flow. So we calculate the potential energy first. So we know that this is the change in potential energy, which is the mass flow rate times the gravity times the change in height. Okay, and that is the values are known from here. So we plug them in. This one we should know. The acceleration due to gravity is a constant that everyone should know by this time. So we plug it in, we calculate for the potential energy, which is given us at 9.24 kilowatt. We do the same thing for kinetic energy using the formula mass flow rate times 1 over 2 velocities, change in velocities or squared. Then we know the values from here. So the inlet is 14 meter per second and the outlet is 5 meter per second, and we plug those in with the mass flow rate and we arrive at 63 kilowatt. So we do the same for a specific enthalpy. For us to calculate for specific enthalpy, we know the value of the amount of work done by the system, which is a positive work, 150 kilowatt. Then the system lost some heat while performing that work, and that heat is minus 8 kilowatt. Okay. Now, and we know the kinetic energy and we know the potential energy. So we calculate the change in enthalpy. Okay. And when we do, we arrive at this value here. Now, for us to calculate the specific enthalpy, and as we know, the specific enthalpy is the enthalpy per unit mass. So what do? We calculate the change in enthalpy per unit mass, and we know the mass flow rate given there, so we use that to divide. Remember, this is written as this, but it also takes account the kilowatts. Okay, the K here means times 10 raised to the power 3. Okay, and we arrive at this. So this is the change in enthalpy, but we are asked to calculate the change in specific enthalpy. So this is where we end with this calculation. Okay. So the second question is the operating characteristics of a steam turbine are given below. So the steam supply rate is 120 kilogram per second, which is mass flow rate. Supply pressure is 38 bar. Supply temperature is 400 degrees Celsius. Torque is 300 kilonewton. Rotational speed is 4,200 RPM. Heat loss from the casing is 1200 kilowatt. Okay, it says calculate the specific volume, the specific enthalpy, internal energy, and the specific enthalpy of the supply steam. Then determine the specific enthalpy of the exhaust steam and its status if it is expanded to 0.5 bar. Ignore changes in kinetic energy. Now, some of the things that we have to do is from steam table. Okay, so since we know the pressure and we know the temperature, we can go to the steam table to find the corresponding specific volume, the corresponding specific internal energy, and the corresponding specific enthalpy. Now, first thing we do, we go to pressure the pressure of the steam coming into the turbine at 38 bar. So what would be the saturation temperature? So going to the steam table, we go to saturated water and steam, and we go for saturated PS, which is saturation pressure, and we look for 38. So in this case, we have P here, okay? We look for 38. So P, we get to 38 bar, and the corresponding temperature is what? 247.3 degree Celsius, and that is the saturation temperature. Now, if we go back to the question, it says that the pressure comes in at 38 bar and 400 degrees C. Now, since the temperature of the steam is higher than the saturation temperature, this tells us that the steam is superheated. And if the steam is superheated, we need to go back to the steam table and we look for the superheated steam. So when we get to the superheated steam column and we look for the pressure, and as you can see here, this is a pressure over temperature reading on this column. So any number above is for pressure and any number below is for temperature. So we look for 38. Now we get here, we can find 30 and we can find 40. So, but we can't find 38. So meaning that 38 falls in between there. One more thing, where is a temperature? The temperature is on this row. So we look for 400 degrees Celsius, then we trace it down. We can only find the values, the corresponding values for those physical properties we are asked to find. So the first one here is the small letter V, which is the specific volume, U, specific internal energy, H, specific enthalpy, and S, specific entropy. So what do? We will use linear interpolation. We can do extrapolation by numbers out with the boundary, or we can use a numbers that falls within the boundary. It could be any number here, it could be 8 and 40, as long as the number we are looking for is within the number range, then we can do interpolation for anything. So what do? We get the values, we use 30 and 40, which is the closest numbers to 38 here on this table. So we get the values, the corresponding values of 30 bar and 400 degrees Celsius for all these properties here. We do the same for 40, then we use the linear interpolation to find the pressure readings for these properties when the pressure is 38. So, and that is what we did here. So we got the specific properties as we see here, the specific volume, the enthalpy, and the internal energy when the pressure is 30 bar. Similarly, we did the same when the pressure is 40 bar. Then we do the interpolation for when the pressure is 38 bar, and this is a formula for doing interpolation. Now, I've already shown you this in Introduction to Thermofluid, and I know some of you may already know how to do this, but if you have questions on this, you can come along. There will be an attachment on the in the lectures and on my UWS on how to do linear interpolation. And if you are still confused on this, you can deal with that during the tutorial period. Okay, so we do the interpolation to calculate for the enthalpy as well. We do the same to calculate for the internal energy. Now, once we've done that, then we move forward with the calculation. So we know the torque, as a a 300 kilonewton, and we know the angular velocity. We need to calculate for the angular velocity. So we know the RPM, then we calculate for the angular velocity, and if we know the angular velocity, multiply by the torque, and that will give us our work done by the system. Okay, we know the heat lost by the system as 1200 kilowatt, and since we are asked to ignore the effects of potential energy, the effects of kinetic energy. Now, what about potential energy? We don't know anything about the height, and if the height is regarded as zero, there is no change in height, then the potential energy is also zero. Then what do? We are now left with change in enthalpy is equal to the heat transfer rate minus the work. Okay, and we plug in the values as given. Then we now find the change in enthalpy, and we find the specific change in enthalpy. And if we know the specific change in enthalpy, then we can easily calculate the enthalpy of the exhaust stream. So from the steam table, we've already calculated the initial enthalpy, which is H1 from the steam table. But since we've calculated the change in enthalpy, then we can add the initial enthalpy at the pressure 38 to this change, and we can find the final enthalpy of the system. Now it asks us one more question. If there is an expansion of the exhaust steam uh, to 0.5 bar, then what will be the new enthalpy of the system? Now, this is us. We can use the quality. You can calculate for the quality of the steam. So if we, with the known variables and the calculated variables, then due to pressure at 0.5 bar from the steam table, we can use that to calculate for the quality. And if we know the quality, and that will tell us the quality of the exhaust stream. Okay, so that will be all for this lecture. And one more thing to note is that in this section of thermodynamics, we'll be going through these three subject areas, which is steam power cycles, the refrigeration, and the gas power cycles. Okay, so we'll be going into this in more details in the next coming lectures. So that will be it for this lecture, and I hope to see you guys during the tutorial time. Please try to attempt all the tutorial questions, and when you get there, I will try as much as possible to answer all the questions you have. Okay, see you guys. Bye.